chi-squared test. Null and alternate hypothesis. One way to determine if there is a statistically significant difference between two treatments is by using the standard error of the mean, which we talked about in the previous section. If the error bars for two sets of data overlap, there is no statistical difference between the two treatments. The observed differences are just due to random chance. If they do not overlap, there is a statistically significant difference. In some cases, it is possible to directly test a hypothesis using a statistical test. The only statistical test that you are expected to be able to use in this course is the chi-squared test. Begin by making a hypothesis and then testing it to see if it is statistically significant. Here are two possible hypotheses for the same phenomenon. The null hypothesis is when there is no relationship between two variables and the finding probably occurred by chance. An example is, cheese kept at room temperature has the same amount of mold on it as cheese kept in a refrigerator for a week. An alternative hypothesis is there is a relationship between two variables and the finding did not occur by chance. It is the opposite of the null hypothesis. An example is, cheese kept at room temperature has a greater, lesser, different amount of mold on it than the cheese kept in a refrigerator for a week. The chi-squared test determines the probability that observed differences from expected results are statistically significant. It tells us if differences in observed results are due to random chance or to some other factor. This is done by proposing a hypothesis and then determining the probability that the hypothesis is wrong. This then provides the probability that the alternate hypothesis is correct. Choosing a hypothesis. The key is to make a hypothesis that generates expected results for comparison to actual results. For instance, if my hypothesis is that each number on a die is equally likely, I can expect that each number on the die will appear with a frequency of 1/6. I can then test that hypothesis by comparing the actual frequency against the expectation of 1/6. The result of that comparison will either lend or reduce support for that hypothesis. In doing so, it will either lend or reduce support for the alternative hypothesis that numbers will appear with unequal frequencies. However, if I were to make a hypothesis that numbers will appear with different frequencies, what would be my expected values? There are infinite number of different frequencies. There would be no expected values. Without expected values, I can't test my hypothesis. It would be statistically untestable. Shown here is the equation and table you will be provided on the AP Biology exam, along with an explanation of the variables used in the equation. On the next slides, we will discuss critical values, p-values, and degrees of freedom before working through an example. So this is the Greek letter chi. Chi squared is equal to the sum of the square of the observed minus the expected frequencies divided by the expected frequencies. And we're given a chart of p-values, which again we're going to talk about in the next slides. P-values of 0.05 or 0.01 and varying degrees of freedom. So p-values. Statistical tests provide a p-value that indicates the probability that a hypothesis is incorrect. If the hypothesis is that there is no correlation between two variables, the p-value indicates the probability that it is false, that there is a correlation. The p-value indicates the extent that the evidence for a hypothesis is statistically significant or not. Typically, and in this course, there are three ranges of p-values which are considered. for a p-value less than 0.05 means that there is less than a 5% chance that the observed results would have occurred if the null hypothesis was correct. This supports the alternative hypothesis. P less than 0.01 means that there is less than a 1% chance that the observed results would have occurred if the null hypothesis was correct. This supports the alternative hypothesis. P greater than 0.05 means that there is more than a 5% chance that the observed results would have occurred if the null hypothesis was correct. This does not support the alternative hypothesis. Degrees of freedom, DF. The degrees of freedom, DF, is the number of possible independent outcomes in the experiment. Flipping a coin has two possible outcomes, so it may seem like there are 2 degrees of freedom. But when a coin is determined to be heads, it cannot be tails. And if it is not heads, it must be tails. Indicating it is heads totally determines the outcome. So only one variable needs to be known, heads or not heads, tails. If there are 2 outcomes to an experiment, but they are completely linked in this way, there is only 1 degree of freedom, DF equals 1. If there are 2 choices, N, there is 1 degree of freedom, N minus 1, as you can see here. If a card can be red, blue, green, or yellow, there are 3 degrees of freedom, since the 4th color is simply not the other 3 colors. You don't need yellow, for instance. Yellow simply becomes not blue, green, or red. The same holds for any of the colors. 3 colors completely defines the 4 choices. In general, if there are n choices, there are n minus 1 degrees of freedom. A final example is on the next slide. If there are 2 variables, let's say heads or tails, and blue or green, then n equals 4, the number of outcomes is 4, and the degrees of freedom is n minus 1 or 3. The possible outcomes are blue heads, blue tails, green heads, and green tails. So n is 4, and degrees of freedom is 3. Once you know that an outcome is not one of the first 3, there's no other choice other than it being the 4th possibility. Critical values. Chi-squared, given by the Greek letter chi, squared, is a continuous function used to test the fit between observed data and a hypothesis. Directly using a graph of the chi-squared function requires integrating the area under the curve above a certain value of chi-squared. For instance, in this graph where the degrees of freedom is 9, the shaded area to the right of chi-squared equals 16.9. So here's 16.9. I've shaded this area. This is 5%. That means that if the hypothesis is correct, there is less than a 5% chance that an experiment would yield a chi-squared greater than 16.9. The greater the value of chi-squared, the lower the probability of observing that result. To simplify the use of the chi-squared test, a set of critical values has been derived for easy reference. The chi-square curves do not need to be used. Those critical values are shown in the below table in the red and blue rectangles for p-values of 0.05 in red and 0.01 in blue. If an experiment yields a chi-squared value that is equal or greater than the critical value, then the corresponding p-value has been achieved. If it is lower, it has not been. Example 1, chi-squared test. The laws of probability state that if we flip a fair coin 100 times, we should get 50 heads and 50 tails. A hypothesis is made that if a baseball cap is worn backwards by the person flipping the coin, more heads than tails will occur. The null hypothesis is that the baseball cap will make no difference, so the expected values E are 50 heads and 50 tails. We do the experiment with the hat worn backwards, and the observed results O are 56 heads and 44 tails. Is this statistically significant evidence in support of the hypothesis on the effect of the baseball caps on coin flipping? This is where chi-squared is used. First, let's test the null hypothesis. There is no significant difference between the observed and expected frequencies, using the equation given on your AP Biology reference sheet. First, let's determine the value of chi-squared. So, for heads, there are 56 observed events. So 56 observed minus the expected 50 squared divided by the expected 50 plus, remember this is the sum of, the other observed result is tails, 44 minus the expected 50 squared over the expected 50. This is 72 over 50. 1.44 is our value for chi-squared. Having calculated chi-squared to be 1.44, we can see where that value lies on our table. There is 1 degree of freedom since there are 2 possible outcomes, heads or tails. So n equals 2, and degrees of freedom is n minus 1 or 2 minus 1, which means 1 degree of freedom. So in our chart, we're going to look at this column where we have 1 degree of freedom. Now we need to interpret what it means that our value of 1.44 is less than the critical value of 3.84, the circled number in the chart for 1 degree of freedom and a p-value of 0.05. So what does it mean that our critical value is 3.84 and that our value for chi-squared is 1.44, which is less than that critical value? This is a bit tricky since the meaning is not intuitive. The lower the p-value, the less chance the results were obtained from just normal coin flipping, and the more chance of a hat-wearing effect. For there to be a 5% chance that the results are inconsistent with normal coin flipping, the value would have been 3.84. For there to be a 1% chance of that, the figure would have needed to be 6.63, where the p-value at 0.01 here. So, the higher the number, the lower the p-value. The lower the p-value, the more likely that the result is inconsistent with the null hypothesis, that this is just normal coin flipping. If our value was 3.84, that would yield a p-value of 0.05. But our result was 1.44. So there is more than a 5% chance that the results were consistent with the null hypothesis. This does not support the hypothesis that wearing a hat backwards increases the number of heads achieved. It doesn't disprove the hypothesis, but it does not provide statistically significant supportive evidence. Science is about gathering evidence in support or not in support of a hypothesis. It is not about proving or disproving hypotheses. Let's look now at a biology example with a little bit more complexity. Based on Mendelian genetics, which you will learn later in this course, we will test if 2 genetic traits are independent. In this case, the 2 traits are long or short leaves, capital L for long, lowercase l for short, and long or stubby shoots, capital S for long, lowercase s for stubby. To test the hypothesis that these traits are independent, we follow the procedure on the following slide. For this example, you don't need to understand how the expected values were determined, just that those expected values are consistent with the null hypothesis. Here's how the experiment is carried out. First, two pure breeding sets of parents are identified and crossed. One set of parents having long leaves and long shoots, and the other having short leaves and stubby shoots. The F1 plants, so the generation of plants that are grown from those pure breeding parents, all have long leaves and long shoots. 1,000 of those plants with the long leaves and long shoots are self-crossed, and the second generation plants, F2 plants, are collected. Their phenotypes are shown below. 382 have long leaves and long shoots. 109 have long leaves and stubby shoots. 112 have short leaves and long shoots. And 397 have short leaves and stubby shoots, for a total of 1,000 plants. Let's look now at determining the expected results if the traits segregate independently. The genotypes for the pure breeding parents were dominant for long leaves and long shoots, and recessive for short leaves and stubby shoots. If the genes are independent, the F2 genotypes should be in the ratio of 9:3 to 3:1 and yield the rightmost column below. So here's what we would expect with independent assortment. 562 of the 1,000 with long leaves and long shoots, 188 with long leaves and stubby shoots and short leaves and long shoots, and 62 with short leaves and stubby shoots, leading to an expected ratio of 9:3 to 3:1. Okay. The null hypothesis is that the genes segregate independently. Since we have both observed values and expected values, and remember where these ratios come from, you don't have to know yet. We will talk more about that when we cover Mendelian genetics, but for now, you can just take these as the expected values. And then, of course, we have our observed values. From that, we can apply the chi-squared test to these data. The observed and expected values from the prior slide are shown here in the table below. In the rightmost column, the calculation of chi-squared values and the sum. So remember, our chi-squared calculation is the observed minus the expected value squared, divided by the expected value. So I do that for each of my outcomes, okay? And then I have to add them. I have to sum them, and I get 1,932. We then use the chi-squared table to determine if that value supports the null hypothesis. Our result was 1,932. There were 4 possible outcomes, so n equals 4. And the degrees of freedom is 1 less than that, so 3. So for a p-value less than 0.01, the critical value circled here is 11.34. Our result, 1932, is greater than 11.34, which was the critical value for a p-value less than 0.01. The higher the critical value, the lower the p-value. You can see that by comparing. If I had a p-value of 0.05, I have 7.81, and for 0.01, it's 11.34. The lower the p-value, the less likely that these results were due to the null hypothesis. Our result of 1,932 means that there is much less than a 1% chance that these results would occur if the null hypothesis were true. Therefore, this is strong evidence that the null hypothesis, that the genes segregate independently, is not true. That makes sense in that the more variance from what the null hypothesis predicted, the larger the value we would calculate. Therefore, the smaller the p-value.